So welcome to our next AI Monday. While everybody is getting seated, aka Zoom is letting us in. Andreas and I will be just starting in a second. We have 64 participants, so really looking forward to the event. The topic of today is Explainable AI in healthcare, and we have some very exciting speakers from different angles looking at this topic, and I'm sharing the agenda in a second. Okay, a few people still having issues there, but I would say it's late enough, so let's get started. Again, welcome everybody to our last Monday before the summer break. Some already, at least in Berlin, arrived. Super curious to see or to hear in the chat maybe where you guys come from. Let us know. We're always, since we're virtual, we always have people from all over the world. I think the last time we had somebody from some island in the Maldives or so that was really so happy for you to kind of let us know where you're coming from in the chat. We're using the chat for Q&A later on, so find the button, put your city or country where you join us from in here, and while we're doing this, as I said before we get into the agenda, we're gonna use the Zoom chat here for any questions. We have 3 speakers. I'm sharing this in a second. If you want to have any questions to those speakers, you can just drop the question into the chat, and Andreas and I will pick them up. But you can also raise your hand virtually. Right? There's a little button there, and then you can actually ask those questions as well with your camera and your own voice. So we're getting this a little bit more interactive and engaging. With that, I think it's time to introduce ourselves. For everybody that has not yet joined one of the AI Monday Berlins as before, with me is today, again, Andreas Schepers from the DFKI, and usually we also have Philipp Günther from Berlin Partner, who unfortunately got sick over the weekend. We're wishing Philipp all the best. But with that, Andreas, over to you.
Yeah, thank you, Juri. As Juri said, my name is Andreas Schepers. I'm the head of communications at DFKI Berlin. Maybe allow me to give you a quick overview over the DFKI. So DFKI is the German abbreviation for German Research Center for Artificial Intelligence. So we've been doing artificial intelligence for more than 30 years now. We have 2 big, or 3, let's say, big sites all over Germany. So one is in Saarbrücken, one is in Kaiserslautern, the other big one is in Bremen. And we nowadays have offices in northern Germany, in Oldenburg. And of course, we're in Berlin. In Berlin, we have what we call a project office, where we are about 130 heads working in different domains, conducting research, also contract research, notably in the domain of speech and language technology. This is the domain our speaker from DFKI, Sven, who will present, will talk later on, is coming from. And DFKI, as I said, 30 years of experience in AI research. We basically try to cover all imaginable aspects of research in AI. And maybe one important thing, although we're very close to the German academia, we are actually a non-profit company. We operate under a public-private partnership model, which means that on one hand, some universities, or by the universities, some German states, Länder, are shareholders, but also we have about 30 industrial shareholders, ranging from SAP over all German car manufacturers to Microsoft, Bosch. Basically, the who is who in the German industry is a shareholder. So this is a DFKI. If you're interested in what we're doing, please check our website. There you will find an overview of all the projects that we're currently conducting. And last time I counted that were well over 200 and something projects that are currently ongoing. So that would be my introduction to DFKI. Back to you, Juri.
Thanks, Andreas. And yeah, Andreas and I were doing this since more than a year now here. So super happy to have you on board again. Usually Philip is also doing some introduction. I'm kind of just quickly trying to take over this. So Philip Günther is the AI Innovation Manager of Berlin Partner. Berlin Partner is sort of the kind of the, yeah, I would say marketing, but then also community building, economic growth company in, or, partner in Berlin. And with that, focusing on, of course, artificial intelligence a lot. He and his team are running the website ki-berlin.de, and yeah, I encourage everybody to kind of have a look. It's quite a good page with lots of insights around the community around KI in Berlin, and connect with that page. There's usually quite some updates around things like getting funding, new events like this one, and so forth. So really worth checking out, and then also getting in touch with Philip if you have any questions or you want to drive your business in Berlin. He and his team can certainly help on this one. With that, I would like to introduce our guest, so to say, because AI Monday always is happy to support special events, specifically around AI in Berlin and in the Berlin community. And today we have Dagmar Tutte with us, who I would like to, who would like to invite you or to participate in the Berlin Brandenburg Innovation Award. And with that, handing over to you, Dagmar.
Thank you so much. Okay, hi. I would like to present you key information about the Innovation Award Berlin Brandenburg. The aim of the Innovation Award of the capital region is the promotion, presentation, and appreciation of future and marketable developments by startups or spin-offs, by founders, established companies, or networked research institutions. And a key idea of the Innovation Award is that today's innovations are tomorrow's jobs. As an instrument of economic development, the competition is geared to the fact that dynamic development is the future. Industries is crucial for the future of the capital region. Next slide, please. Up to 5 outstanding products, processes, services, and non-technical innovations are honored each year. The awards are endowed with 10,000 euros each. Companies, founders, startups, cooperation partnerships from science and business, and individuals and teams, especially from universities, can take part of the competition. Next slide, please. It is important that the innovation can be assigned to one or more clusters. These clusters are part of the innovation strategy of the states of Berlin and Brandenburg, and the clusters are healthcare, industries, energy technology, ICT, media and creative industries, optics and photonics, and transport, mobility and logistics. And those who meet these requirements can apply online. In the first form, you have to enter your contact details as well as the name and a brief description of your innovation. And you will then receive a personal ID by email and a link to a second form in which we ask you to answer 3 questions about your innovation. And the jury will then select up to 10 nominees, which will be announced in October. But in order to be able to award the best ideas at all, we need many courageous people to participate. We use various social media channels to call for applications, provide help and tips, share events, and let former award winners speak about their experience. And all channels can be found on the website, and you are also welcome to follow us here and share interesting content. Next slide, please. It is also possible to become a partner of the Innovation Award. Here you can participate financially or make contributions in kind. There are various possibilities and different partner packages, and the conditions can be discussed in a personal exchange. And here you can see who is already partner. Next slide. Here you can see all the important dates for this year. The application phase for the Innovation Award runs until the 21st of June. On October 8, the press conference will take place and the nominees will be announced and pitch their innovation live. And on November 26th, the award ceremony will take place and the winner will be announced. Next slide. And you can find all further information at innovationspreis.de. That's it. Thank you so much.
Thank you, Dagmar.
Super cool. Thanks so much. So if there's any questions to Dagmar, yeah, feel free to either reach out to those addresses, right? Or immediately just ping her on the chat here. I think she's going to stay for a little bit. Maybe there's some more questions. With that, I would say, let's get started. Time for our agenda today. And I'm super happy that we have so much brain power here in the room. We're going to start with Dr. Wojciech Samek. He's not only working for our Fraunhofer Heinrich Hertz Institute, but a lot of more. But I will introduce Mr. Samek in a second. Second, we're super happy that Dr. Sven Schmeier accepted our invitation, and he's coming from the DFKI, and he's talking about the project science. We're talking about that also in a second. And then last but not least, we have Dr. Günther Hoffmann from MedaPlus, which is a startup in the healthcare area, specifically focusing also on beyond other stuff, but on explainable AI. So we have Mr. Samek kind of giving us kind of a broader intro into what is explainable AI actually, and specifically was focusing on healthcare. Then we have Mr. Schmeier talking about the project science, which is going into that direction as well. And then we have a real use case at the end with Mr. Hoffmann sharing that one, right? Yeah, with that, I forget one thing, right? The reason why we're so late today is that we're a satellite event of the Connecting Digital Health event, DMEA, which actually started today, and we didn't want to interrupt with their schedule. Hence, we were asked to start a little later than usual. But I think that's why it might be even fine for not conflicting with the usual work priorities. Anyway, with that, let me introduce you to Dr. Wojciech Samek. He studied computer science at Humboldt University in Berlin here, but also on Harriet Watt University of Edinburgh. He received a PhD with summa cum laude from the Technical University of Berlin, so a real Berliner, so to say. And he also founded the machine learning group at Fraunhofer Heinrich Hertz Institute. There is much more you can talk about, Mr. Samek, probably for the next 5 minutes. I will stop here and hand over to you. And yeah, super interesting, interested to hear about yeah, explainable AI, interpreting, explaining, visualizing deep learning. That's what you also wrote a book about. Super happy to have you here today. Thanks so much for coming.
Yeah, thank you very much for this kind invitation. Let me share my screen. Yeah, so today I will give you a bit of an intro into explainable AI and also talk a bit about things beyond. So especially what we can do with explanations. So the first question, explainable AI, you should ask yourself is, what exactly do you want to explain? Do you want to explain the data which you have? Do you want to explain the model, what it has learned, what it is representing, or do you want to explain a particular prediction? And there are different methods, like for all these things. Classically, people develop methods for visualizing data, for get into the structure of data. These methods are usually not counted as explainable AI, but they also give you some nice insights. There is some recent work which aim to better understand the models we are working with. So for example, to understand individual neurons encoding, or what properties, what categories a model has learned. And there is this domain which I will talk about today, which is also my field of research, is understanding individual predictions. So if you have, for example, an image of a particular digit, in this case a 3, and your model says this is a 3, you may want to know why the model has arrived at this classification decision. But even if you just constrain yourself to this definition, there are more detailed questions you have to ask yourself. So for example, level, you should get the explanation. Do you want to explain in terms of pixels, in terms of subpixels, in terms of objects? Because all this can give you different information. Also, like especially in the medical domain, if you have like a time series of ECG data, one level of information can be more meaningful than the other. Also, you should ask yourself, explaining the decision versus like anything else in the world, or do you want to have a contrastive explanation? So why the model thinks it is a 3 and not a 5, or why the model thinks it's 3 and not an 8. So these explanations will differ. And whenever you talk about explainable AI, wherever you use these methods, you should be aware of what you exactly want to explain. There are also like things like, do you want to have individual explanations for each feature, or do you want to explain interactions between features? Do you want to also get the information what, for example, speaks against this particular 3 in the image, or do you just consider positive information more relevant? So there are all these different things which have to be clarified. If you work with these methods, you should be aware of what you get when you apply these methods. So the question is now like how to explain. So if we think, okay, let's explain individual predictions, like what can we do? And there are different types of methods proposed in the literature. Probably the most simple ones are perturbation-based methods, where you, for example, occlude certain part of the image or of the input, or perturb it in a way, and then track the reaction of the model. And if there is no reaction, then probably this part was not important. If there is a breakdown in classification decisions, then this part was probably important. So you can find this out by indirectly like perturbing the input. But as you see, this method has some disadvantages. You have to do it like many times, and you may introduce some bias when perturbing and so on. Another class of methods is function-based methods, which are based on gradients. For many machine learning models, you can compute gradients or simple quantities of the function, and many people construct explanations from that. And although this is a valid and very efficient approach, it has a disadvantage that, especially for deep neural networks, gradients are very noisy and have some problems. So there is some work showing that in the deeper the model will get, the more uninformative the gradients get which you have. So there is this gradient shattering problem, which makes your explanations not very accurate. There are like approaches to sample and to train a surrogate model. So the intuition here is that if you cannot explain the complex model which you want to explain, just train a which is explainable, which kind of approximates the prediction which you are interested in. This is also like quite a popular way to explain predictions, but as you see, you have to train another model to explain the model of interest, which is time consuming, which requires computation, and also like you are not sure that you are really explaining the model of interest because you are just explaining the surrogate. This fourth category, which I mainly work with, are structure-based methods. So we have proposed LRP as one of the first methods to explain predictions. And the idea behind this is that you explain your models by using the insights of the model, by using the structure. So these approaches are very efficient, provide good explanations, but the price to pay is that you need to know the details about your model, the model's internal. So these methods are not model agnostic. So how it works, just very briefly. So you have some input, then you get the prediction. Some of the neurons on the way get activated because they encode something related to the input. And the idea is that you want to redistribute now the output back to input space and do it like in a very meaningful manner. So you start with the output neuron, in this case, the rooster, and move layer by layer backwards. In this, we came up with different propagation rules. This is kind of the simple one, which just takes into account the weight of the between the layers and also the activation. So the intuition is that the more activated the neuron is, the more relevance it should get, and the higher the weight, the more relevance should flow according to this connection. There is some theoretical interpretation on that. I won't go into details here. So if you have questions, we can discuss, I can explain later. But in the end, what you get is you get a decomposition of your predictions in terms of input variables. So if you have prediction is rooster, then you get an assignment of relevance values to every pixel, which you can then visualize as a heat map. Okay, so now we clarified like how to explain. So a key question is like, what do we need the explanations for? Of course, you can look at them. You can try to verify if your model predicts correctly. This is something which is, I would say, also very relevant in healthcare. If a doctor is using like an AI support, then of course it's additional information which is very, very valuable. If you understand the reasoning of the system, if you understand the reasons behind the decision. And in this case, you see like a model which was trained very successfully. In this case, it even won an international challenge, a very prestigious one, but the model classifies not as expected. So it classifies ships by the presence of water, it classifies trains by the presence of tracks, and it even learned an artifact in the data. It classifies horse images by the presence of a copyright tag. And this copyright tag issue was unknown for, I think, 8 years. And because nobody looked at the data, nobody saw that there is this problem, the systematic problem, and people just reported the performance values, accuracies. And by getting some insights, we showed that this model learned something which works data set, but which does not generalize because it's an artifact. And we think like explanations are a very good tool get this information. So you can see from one classification, you can, in the extreme case, you can see that something is strange. Another reason to use explanations, especially in medicine and the sciences, is to gain novel insights. So here we trained the predictor, a decoder. So the task was to decode 4 different classes from an fMRI signal. So this was a collaboration with some neuroscientists. And our deep model not only like decoded very accurately, comparable to, or even better to standard methods used in neuroscience, but we could also get explanations for every time step for every individual, which in the best case allows you to come up with some new hypotheses about the data, about the process at hand. So we are currently still looking at the data and trying to understand also the dynamics in this fMRI data and the processing in the brain. So this is also like very interesting way to use explanations. Another one here, we use explanations for also like together with some epidemiologists. So the task was to predict risk with different factors like gender, or sex was a factor, or if you use drug 1 or drug 2. And what we did is we trained the model. The model was predicting correctly in most cases. And then we explained for every participant, we explained what was relevant, and we clustered this explanation. See here that in the data which we looked at, there are 3 different groups with different factors with different risk factors for a disease. So you can get some insights by clustering, by analyzing this explanation. This is something which goes far beyond just looking at them individually. We also like used these tools to study our model train. So in this case, we trained a model which was playing Atari. And you see on the left, there is a red part at the bricks, which is deemed relevant. And you see why this is deemed relevant, because the model tries to place the ball, to build a tunnel and place a ball over it, so it can get a lot of points without the risk of losing the ball. And we kind of analyze the training process. So on the right, you see the curve, 3 curves showing the relevance of the ball. So the green line shows on the x-axis, you have the training process of the model, the training epochs. And you see that the first thing the model did is to look at the ball. It learned that looking at the ball is a good strategy. Then it looked at the pedal, at the thing which you use to control the ball. And after 50 epochs, it got the trick with the tunnel. So you can like analyze the training dynamics with these tools. Something which is, I think, not so much done so far, but which is very also important to get some trust into your models. Yeah, you can improve your models. For example, if you know that there is an issue with the model, you can try to clean the data, try to improve it. For example, on the left, you see that this is data from ImageNet. And we found that some of the images in the class stethoscope has like a cut, and the model learned to use the high contrast to classify these images as stethoscope. So you can, if you analyze this, if you automatically detect these things, you can try to clean your data or remove this example of these artifacts. This is something we're currently looking at. Or you can also like directly integrate explainability into the loss of your model. Also something which is very recent, which we are very much interested in. So we now look really at what can we do with explanations beyond just explaining. And finally, some work which we did with the TÜV-Verband and BSI, Bundesamt für Informationstechnik. So we looked at ways to audit an AI system. So to certify that it does exactly what you want it to do. How can a framework look like to certify and audit a system? So we wrote a white paper recently about that, and explainability is also like one important component. If you want to audit a system, if you want to certify it, you should better know what it does, and you should understand the reasoning of it. And we are also part of some international initiative founded by the International Telecommunication Union and the WHO. And this focus group AI for Health is exactly developing such a framework, testing framework, auditing framework, certification for AI applications in medicine, in health. So we exactly like are looking at this issue, like how can we audit a system, and explainability is also like a very important ingredient here. And this is an international initiative. Also, like regulators like GFAM or FDA are also part of it. Yeah, with that, I would like to recommend some reading. So we recently published an overview paper in Proceedings of IEEE. There is a book which I edited with some colleagues 2 years ago. And we also have a couple of other papers which are very accessible and give you some overview of the problems, and also like the opportunities which you can get with Explainable AI. And we have a web page where all the software and tools and papers are. If you check it out, you can find all the work. And with that, I'm happy to take questions. Thank you.
Cool. Thanks so much. This is Samek. I think there's one question from Injun Leo, and I would just ask you to ask the question yourself, Injun.
Oh, yes. I was just going to ask this question, not only to this speaker, but to other speakers. But my question is, if you can explain from healthcare scholarship before AI, what were the scholars debating on technology? And after AI, how does the AI fit into the healthcare debate? I'm happy to elaborate that further. Like healthcare could also include medicine. Yes.
So what was the question? Like before AI, if scholars were debating on technologies? I think so. I think every in healthcare, people like before it was established, people were debating about that, and some of them like were stressing the opportunities. Others maybe not convinced from the beginning. So I think this is a very normal process to if tools are introduced. To have some discussion, and also like sometimes it needs a generation to take up these new tools, and I think the thing which we saw also like before AI. So what are the learnings from the auditing of AI collaboration? Yeah, I think there are many different learnings. I think one thing which we learned is that it's a multifaceted problem, so it's not so easy to grasp. Also, it requires like activities from different sides, so you have to start the process like from the beginning. So not only after training of the models, you have to care about the data quality, about the labeling of data, about the acquisition of data, about all the things which come, about the definition of a problem, about all the things which come before actually training a model. This is something which we learn, and I think there is also like a component of maybe there won't be like 100% safety, and especially if you think about adversarial attacks and these things. So I think in the end, you also have to think about which risk are you are you able to take, or what is the average benefit and maybe the average cost of risk? And this can be very application dependent. So for some application, maybe it's fine if the AI is is only 99% safe. For other applications, it is not. So it's a very complex discussion.
If I'm allowed to ask a follow-up question, do you think, like for AI in health especially, I mean, there are the obvious benefits of AI spotting early signs of some illnesses in pictures, of course, but if they, do you think they will be unusable in the praxis if they aren't designed with the auditing process in mind from the beginning? Like, will it be impossible to certify them at the end when it's done, like when the research is done and the algorithm stands and everything is set, then it will be impossible to certify?
Yeah, I think, I mean, FDA has already certified a couple of such systems. So I've spoke to the guy who was kind of responsible for that, and I think there is not only like the issue of like certifying a particular system, but also like how to deal with, for example, updates. So do you allow the system to learn further, and once it's certified, how can you be sure that after some updates, it will still like fulfill your certification criteria? So I think this is something which one has to take into account from the beginning, also like in the design of your algorithm, in the acquisition of your data, something which is maybe not usually done today, but which I think people will, once things are more professional and once standards are, international standards are available on that, or like successful examples. So these processes will also, I think, be more standardized and there will be less variance and less noise in that. But I think there is a strong need on these kind of guidelines and also like criteria and processes from the beginning of your process through the deployment phase and training phase and so on.
Thank you.
Cool. Thanks so much. There are some more questions in the chat. So maybe Mr. Samek, if you may want to have a look and maybe respond to some of those. Otherwise, one of the questions was whether we can share the presentation. I'm not sure, but definitely the event will be recorded, and then you can have that during the week. And then as I maybe outlined in the beginning, if you haven't been there, so we're gonna have some networking time afterwards, and then you can grab Mr. Samek to maybe discuss more of the questions. Just a little bit cautious of time right now.
Yes, so maybe like a short comment on this post-hoc explainability. So I'm mostly work on like methods to explain models post-hoc, but it's also like a very interesting field to integrate explainability into the model, or integrate it also from the beginning, something which is also very, very much of interest. And I think it should be taken into account when talking about explainable AI in healthcare.
Perfect. Cool. Thanks so much. And with that, I would say we're going to hand over to our next speaker, Andreas.
Yes, thank you, Juri. So I'm not the next speaker, but I have the pleasure to announce the next speaker, who is Sven Schmeier. And Sven is a chief engineer and the associate head of the Speech and Language Technology Lab at DFKI in Berlin. Sven is not only a computer scientist by training, he also holds a PhD in computational linguistics. And he's also, I sometimes call him a serial entrepreneur. So he was involved in actually a number of startups that he co-created here in the Berlin area. So with no further ado, I would like to introduce and present Sven, who will talk about chains. And maybe just as a first question to you, Are you sure, Sven, that it's actually pronounced chains? Because Yuri was talking about xanes. I don't know how to pronounce it. So what is this miraculous project about, and how do you pronounce it?
Yeah, thank you, Andreas. I hope you can hear me.
Perfect.
Okay, cool. Yeah, this is a very difficult project. So even the name is very difficult. So there's actually no real agreement on how this is pronounced. So I say chains because it's easier than xanes. And most people I know are calling it chains. But yeah, actually there is no real right way to do it. Yeah, but speaking of chains, this is a project which started in October last year. So it's pretty young. It's for 4 years now, and we are conducting research there within the DFKI. I think through all the places, all the sites of DFKI. So Saarbrücken and Berlin and Kaiserslautern and Bremen and also Oldenburg and Osnabrück, they are all involved in this project. And so the main title of this project is Explainable AI using narratives. Okay, so narratives is one of the central words besides explainable AI. So what are narratives? So since the 1990s, narratives have been used to describe some kind of sense-making story that influences the way the environment is perceived. It conveys values and emotions. It's usually related to some kind of nation state or specific cultural area and is subject to change over time. So narratives are changing over the time. So in this sense, narratives are not just arbitrary stories, but they are some kind of established narratives that endowed with some kind of legitimacy. And however, in this project, we are not going that deep. We define it more like using natural language to explain the behavior of a system. A system, especially in a data-driven system. So why is that such an issue? The reason for that is the world is complex. We all know that, and the world in healthcare is also very complex. And not only the system that needs to be explained play a role here, but also the person to whom it will be explained, and of course also the purpose of the explanation. So why do we need to explain a system behavior? And in the end, especially in healthcare, it's all about trust. So can we trust the system? Of course, for us, it's also curiosity. We want to know how it works and why. And in the end, even it has some financial or practical impact. So as we heard before, if we can explain the system's behavior, we can maybe certify it. And if it is certified, we can guarantee that it works in principle. However, we tried this kind of guarantee much earlier and found out that most things, the interesting ones, are not even decidable, and hence there is actually no proof whether they are working or not theoretically. If we would live in a mathematic world, this is much easier, by the way. Here we have all well-defined the world, and we can use mathematic engineering to prove things. And AI systems have been very useful, starting already in the early 1950s to explain mathematics. So for example, there was a system, the logic theory machine in 1956, which was a deduction system for the propositional logic and of the Principia Mathematica. We all know at least the name of this book series, so to say, which was, and the system was developed by Newell, Simon, and Shaw. So they were using this system to prove theorems of the Principia Mathematica. So it was early start. So in the end, this means we were very good in finding out things and explaining them for rather the complicated stuff in mathematics already in the 1950s, but we still struggle to explain machines or algorithms that can perform well in real life problems. And the reason for that is, of course, as I said before, the world is complex and things are also working much different in machines than in humans. So in case of the data-driven methods, it is machines think in statistics and humans think in causalities. And because of this, we see that computers often enough fail in tasks that seem to be very easy for people. Just think of the accidents in autonomous driving cars. We've seen that in TV, for example, which often seem to be avoidable if we let a 6-year-old child drive that car. The 6-year-old child would not have driven into some lorry, something like that. Or when you give an answer to a dialogue system or a chatbot, and this system tells you it could not understand what you said. You just answered the question that was asked by the system, and the system cannot understand what you say. So you see there is some main difference between the things, how we handle stuff in the world and how machines handle stuff in the world. Of course, speaking of artificial intelligence, we all know that machines are not intelligent. They also do not think or learn. These were merely marketing buzzwords to get the funding. Instead, they optimize their behavior in order to fulfill the task. And that's what chains is all about. Lots of other explainability approaches also are all about provide explanations to show the user, hey, you can trust me because I show you how I do it. And then you can use your own intelligence to judge me. And with this in mind, we are planning to combine explanations in natural language for 3 different scenarios in chains. So the first scenario is cancer treatment, especially finding melanomes that result from skin cancer, and explain why we think this is some kind of bad thing on the skin, or we try to explain why we think this is a melanome, or the machine must explain. The second use case that we are doing is autonomous driving, where we try to use natural language to explain streaming sensor data. You know, when the car is driving or an autonomous car, there's very much data coming in, and we try to make sense on how this data is perceived. And the third use case is in construction engineering, in which we want to research how narratives from various online how-to descriptions, you can find them in the internet everywhere, can be automatically transformed in so-called semantic models. These models describe how complex activities can be represented in the form of kind of simple actions, and how such models can then be used for automatic sensor-based recognition of humans and machines cooperating in some kind of complex physical activities. So we have not only healthcare, but we had also 2 other use cases. The target group, which is interesting for the explanations, will be the developer and the domain expert. So it's not for the layman, it's for the developer and for the domain expert. And the technologies on how we try to achieve this will, of course, vary. We actually started the research, so we, of course, have no solution yet. And in our speech and language technology group, we are currently experimenting with different explainability approaches, some which overlap to Wojciech's talk before, which is pattern attribution, approximations of integrated gradients, and a very new idea are the empirical explainers. This is a paper conducted by colleagues of mine. One is Robert Schwarzenberg, and the other is Niels Feldhuis. They had this idea of the empirical explainers, and they predict the information. So the empirical explainers predict the information that is needed for the complex techniques of explaining things, and such reduce the computing time a lot. So just to give you 2 examples, which can also be found in the paper they both wrote. We were generating expensive target explanations for the official IMDb test split. IMDb is the movie database, and we had we did the training on 25,000 longer instances with integrated gradients and 20 samples, and this took us more than 7 hours on NVIDIA Titan 5 GPU with around 12 gigabytes of RAM available. So at least it was 26 hours, 22 minutes for training 22,000 training instances. The second example is we were generating shapely values, which is also very prominent explanation method for the Stanford natural language inference test flit, again with 70 samples. And this took us 48 hours on a now even better machine, NVIDIA Quadro GPU. Yeah, it was about 600 GPU hours for at least some kind of 100,000 training instances. And in contrast to this, so we had 7 hours before, and then here we had 48 hours. With the empirical explainers, we only need 7 minutes. 7 minutes to predict the data that is needed for these shapely values and the integrated gradients to conduct their explanations. Yeah. Okay, and of course we introduced with this some error. Yeah, you always introduce some error if you are not using the real values, but you are using some predicted values. But this error is very, very little. You can read it in the paper. I will post the link into the chat. Yeah, and so however, so far we just tried this out on text data. So we want to try this out to visual data in the Chains project, but we are not that far for the moment. So we did also not use it for sensor data. So we will see how that will work out in future, and we try to do our best to have some self-explaining machines in these 3 scenarios near future, hopefully. Okay, and that's all I can tell you. Thank you.
Thank you, Sven. So that was a fast ride through the aim of the Chains project. Thank you very much. So I'm looking at the chat, trying to find out whether there are questions specifically to your presentation here. And I'm not quite sure. So if there is, please raise your hand or put your question into the chat. Sven just shared the paper he mentioned. So no question. Must have been a brilliant presentation, Sven, as usual.
Yeah.
I have a question. Yes.
Very good. Go ahead.
Okay. This is something I asked other speaker. I wanted to get your take. From healthcare scholarship before AI, where were the scholars debating on technology? And after the AI, how does the AI fit into the healthcare debate?
Yeah, I'm still not really sure what the question is, but I try to answer as far as I understand it, right? So when you're talking about AI, I think you're talking about the neural approaches of AI, because there was AI very early in medicine, already in the 1970s, where they were used, for example, some kind of expert systems that helped the doctors to find out what disease people were suffering from by entering or asking the people or entering the symptoms. So this was already some kind of AI, but I guess you are meaning the neural part, so the machine learning neural part, right? Am I right?
Yes, that's correct. Yeah, I'm just
okay.
Yeah, I'm just kind of looking at what are the from a healthcare scholarship, what are some debates on technology even before AI? Now AI comes in. Where does that fit into their healthcare debates? You talk about trust as an issue that comes when it comes dealing with AI. So maybe that's perhaps one of the components. Yes.
Yeah. So what we are also doing, we have a project where it's about some kind of ethical things, and also things that are concerned with getting into the law things. So who is responsible when there is some kind of mistreatment of some patient? Yeah, is it the machine or is it the doctor, or who is in the end the responsible guy? And this is really a difficult debate, because when the doctor relies on the algorithm or the AI part too much, then maybe things go wrong, and the doctor needs to explain himself. So we want to avoid this by giving a machine some kind of good explanation so that the doctor understands how the machine comes to the result, and then also puts some trust in it, and can understand why the things were judged like they were from the system. And with this in mind, I think it's really difficult, and is kind of research both on the technology, but also on the ethical state of the art. Yeah.
Okay, are there further questions? If this is not the case, Sven, I'll say thank you again. And I'll hand back to Yuri. Is Yuri there? Yuri is there.
Yes, I am. And yeah, so thanks so much, Sven. Super interesting topic. Really exciting. And as we said in the beginning, if you come up with some questions afterwards, also Sven will be around for the networking afterwards, so you can grab them and have further kind of deep dive questions if you don't want to kind of raise them here in the big round. But with that, I would say thanks so much. And we're kind of getting to our last speaker, which is Dr. Günther Hoffmann from the company called MedaPlus, which is a startup out of the healthcare area. Günther is actually the founder and CEO of MedaPlus, which is even a Berlin-based startup. And we're always super happy to have Berlin-based companies here also presenting themselves. And I think with not much more introductions, I would just hand over to you, Günther, and then leave it to you to explain what is MedaPlus, what you guys are doing, specifically with the focus on explainable AI. Thanks so much for coming.
Yuri, thanks for having me tonight. So my name is Günther. I'm the co-founder of MedaPlus. We are a Berlin-based startup, and we are active in AI for healthcare professionals. My co-founder is Ulrike. She's a medical doctor, and I will try to share some insights, some real-world insights when you try to roll out AI-driven and data-driven solutions in the healthcare sector, which is not trivial. And we've heard a lot of we've got a lot of interesting background and information about how AI works and how this could all be applied to the medical sector. And I hope I can give you a better understanding of how it actually works in the real world. So a product class, or from the helicopter perspective, very high flight level, a product class of clinical systems are clinical decision support systems, CDSS. And they've become vital for healthcare organizations, and mostly with the motivation, some to improve care delivery, and some to actually analyze and flag anomalies. So in a broader context, that is improving patient care. And some suggest the next steps for treatment, and that would be personalized treatments. So that is all noble and a great motivation. But what we see in real world examples is that before AI and any AI-driven solution actually delivers the expected value, and actually what we see is that a lot of AI-driven applications don't deliver the value that is expected and needed. And why is that? And here are some reasons that we found in real world environments. That is, you run into very high complexity in terms of use cases, and particularly in a clinical environment. And it's not only am I right or wrong about predicting a certain medical features. It's about the legal environment, and we heard a lot about this in the two earlier talks. what we often see is there are silo-like data structures. There are everybody is used to roll out commercial off-the-shelf software, but AI-driven software really works very differently. And there's a lot of experimentation involved to get an AI-driven or data-driven system running. And that's very different from a commercial off-the-shelf software. So really, if you want to roll out an AI-driven software in the healthcare environment, that's a completely different process. And it doesn't work straightforward. There is some, and even if you get that straight, there is a lack of integration. So yes, you do have standalone systems, and it may predict some skin cancer or whatever, but typically it's not integrated. And there is a lack of scaling. So how do I not get this only for one department, but for multiple departments? Not to think about getting this rolled out across multiple healthcare units, hospitals, or internationally. So these are some real-world issues that we ran into. And so our approach was that we provide software that helps healthcare organizations to actually build enterprise-scale AI applications for medical processes. And actually, we've done that before, and we are doing this right now in other industries, where this works very straightforwardly and which brings in measurable success and benefits. It's a different story in healthcare. So what we're trying to do with our platform approach is to automate the building and the validation and the integration and then the operation, and then also the securing and the scaling of AI-driven applications. And to give you a better understanding how that might work in real-world environments and where the AI comes in, let me run you through some of the use cases that we've been working on, and some of them we are rolling out. So if you think about clinical processes, then a lot of focus is on, oh, how can we get great analytics, and how do I predict that skin cancer or some other conditions. But again, AI has to be there and it has to work, but really it's only a part of the solution. And it's a small mosaic in a pretty broad and large infrastructure that has to work. So before we can actually talk about applying fancy AI technology to analytics, we really got to make sure that we get the patient data into any kind of system. And how does that work? And that's completely non-trivial. Just to give you an example, many of the hospitals, they're not even digitized yet. They have handwritten paper documentation. How do they get handwritten documentation into a system to later analyze the data? So that's one of the things we struggle with. So one of the use cases is that we read unstructured case histories, for example, from multiple sources. And that's, again, touching the issue where a lot of information is distributed in very different kind of systems. You have to aggregate them, read them in, and then you can start using AI-driven technologies like use NLP, for example, entity extraction, to, in a very first step, convert that unstructured data into something more structured. I'm not even saying structured data, but into something that is more structured. And the other issue is simply merging patient data from multiple sources. Like you have measurements from IoT devices. That's technical. I'm not a medical doctor, so I use like IoT devices. But it's like, what is it, blood pressure measurement or auscultation data. So all of this data needs to be, it comes from different sources, but it has to be consolidated in one place. So you can actually start analyzing that with AI. And once you got that running and you've got that issue solved, then you can start working with fancy analytics to identify patterns, right? So patterns in patient data, patterns, and let's say with medication interaction, Or one of the use cases that I will run you through briefly in a minute is auscultation sounds. So we've been working with digitizing the auscultation process, and then we have lung sounds and heart sounds that can actually be analyzed with explainable AI. And then once you got that straight, then we can talk about alerting and explaining, and simply raising a flag and say, hey, listen, that's something wrong with the signal here. Hey, doctor, have a look at this. And once you got your analytics straightened out, then, well, that's great that one doctor has gotten that information, but really in the next step, he may want to share that data with somebody else. So sharing that findings with colleagues to get a second opinion, for example, and to get the compliance documentation straight and so on. That at that part of the process is not very much AI driven, but it's important to get the AI driven application running and accepted actually in a clinical environment. So how is all of that relevant for, let's say, enhancing a clinical workflow or bringing and adding AI-driven technologies into a clinical environment? And to give you a brief overview, I'll run you through some of the use cases that we've been working on. And first use case is to integrate and to analyze unstructured data from multiple sources. So what you see here on the right-hand side, these are release documents from a hospital, and fortunately, actually, they're digital already, and often you don't have them in this digitized form. But in this case, they are digital, so we can read them, and we can try to run NLP or entity extraction to identify medications or other conditions. So simply to have these entities to work with them later on in the analytics process. And this very simple step, basically preparation for AI-driven solutions. Simply, if you use that information and consolidate it in what we call an intelligent health desk that allows the physicist or a nurse or somebody else who's looking at the data, simply to get that data in a timely fashion, or to get a number of interactions displayed, that is a great benefit. And at that point, we're not even talking about AI yet. The AI part comes later on in the process. And here's one of my most favorite use cases. That is, we're digitizing the auscultation process. So what we did is we actually developed, we started out with the objective to read in digital auscultation data, because we figured, well, by now there should be a lot of digital stethoscopes around there, and we just work on the digital data. Turns out that's not the case. So we started early on and in the process and developed our own digital stethoscope and stethoscope digitizer. So with that, we started recording sound samples from lung sounds and supported doctors in building up what has now become a pretty large repository of lung sounds. And but really, what's an AI going to do with the lung sounds, right? So you have to have a human expert preparing the data, so you can actually use it for AI-driven analytics, and in particular for explainable analytics. And so we had real doctors sitting on these real data and actually annotating this data to identify the anomalies like weasels or cracks or any other anomaly that you could pick up in sound data. And we use then that data to build models that would be capable of picking up these anomalies and flagging them to physicians or nurses or whoever is producing this auscultation data. And that and just that very small use case opens up a pretty broad range of application scenarios. So what we see in real world applications is that, for example, a nurse picks up a sound sample, and then she doesn't see or hear any anomalies, but the system picks up an anomaly, and then it would flag it, and it would show, hey, look, this is an anomaly that I found, and then either the nurse or practitioner listens in again and can validate if this really is an anomaly, and if it should be followed up on. And what we again saw in real world applications is that you really have to be a very experienced physician to pick up anomalies. So not everybody finds these anomalies in sound samples. So a lot of times the system would signal that there is an anomaly, but the doctor would say, oh, it's not, right? So we ignore it. But if you had an experienced specialist listen into, they would acknowledge that this is really an anomaly. So you have to cover a lot of ground here and support multiple functions with your AI-driven system. So I don't want to bore you with any tech details here, how a platform works. We're currently with the German accelerator in Singapore, actually, to validate the markets there. We've been named one of the 100 most innovative startups in Germany. Got some awards as well. And I think what's really important is we have in our team we have two specific functions, and these are medical doctors that know how the medical processes work, and they understand how their colleagues work, and they understand what they really need. And that allows a second part of the team that is more analytics driven to actually produce this kind of result that is then accepted by a medical doctor. And again, that introduces a number of issues that need to be solved. So I hope I could give you a brief rundown and share some insights into how AI-driven solutions can work and do work in real-world scenarios. So yeah, thanks again for your attention, and I'm looking forward to receiving your questions.
Thanks so much, Günther. Really interesting. I also like a lot the how do you call this, Auscultation use case, right? Quick question, while there's maybe more questions popping up out of the audience here. This, in the sense of explainable AI that we had with Sven and also Samek, it was all around like the AI is producing some results, and we want to understand, okay, how did the system actually derive to that result, right? And how can we explain which like input attribute kind of was kind of responsible, or how did the AI come up with this result? Is that something that specifically was, for example, this use case that you've shown, that you also look into is like, okay, what's the data out there, the anomalies, or the sound bites that are kind of being used, or that you need to look into in order to kind of also improve or to kind of validate whether this this prediction is actually right in that sense.
Yeah, I mean, this has been a pretty interesting ride, because from looking at it from the technical angle, right? So how do you get the model right, and is it black box, is it white box, and what's the explainability exactly, and so on? You can get completely lost in that universe. So what we figured, or what we found, is actually the most important part if a practitioner is supposed to be working with the system is, look, you just got to show him that this is the anomaly that the system has identified, and here is the sound sample. Now, let the practitioner validated, right? And then he can, the practitioner decides if it really is an anomaly or if it's not. And as I mentioned earlier, again, it sounds straightforward, but it's not, because if you have an inexperienced practitioner, they will probably, they will not see that this is an anomaly, and they will ignore it. And then if you ask an experienced practitioner, then they see the anomaly. So really, I think the key aspect is how is the practitioner interacting with the system, and what kind of information is being shared with the practitioner. It's not so much the AI-driven method that's coming in here. It's much more, how do you set up the UX with the user?
Yeah, no, I totally can understand that one. Cool. There's two more questions popping up. One is super broad one from Injun. What are ethical issues in AI and healthcare? Maybe to kind of narrow it down, maybe specifically from your perspective, or did you kind of get into ethical issues in your work with MedaPlus in the past?
Well, gee, that really is a broad question. I would rather pass it on to somebody that is more qualified than I am. But we've run into not issues, but questions. It's like, okay, so for example, the Auscultation database that we have, this is mostly coming from, obviously, from Caucasian patient base. So the question is, so does it also work on an Asian database? So now we're exploring markets in Singapore. So the question is, okay, so do we have to have a different database with Asian based lung sounds, and do the same models apply? So these are real world issues that we need to address. I hope that that answers somewhat the question.
Yeah. Well, yeah. I think Injun, you may respond in the chat again as well. Jumping to the next one from Christian Pflug, which is kind of going back to the question around experienced physicians, and how do you guys use their feedback and experience and to kind of using that for kind of improving the system, but using different data, better training data, better real data. Is there kind of this kind of human learning process that you built in, and how important is it for you? So I can't hear anything anymore. Is it me or is it Günther?
I'm still there. Maybe we lost Günther. Let's see.
Yeah, I think we lost him, unfortunately. Well, let's see whether he comes back. Let me quickly. Yeah, let's see whether he comes back, and I can just quickly share my screen and maybe start slowly, because there's not more questions. Slowly getting into wrapping up today. I think one of the things that I want to, because it's also related to today's topic, we have with our chapter from NRW, from I think close to Bonn, and Lippe, we have the topic coming up, AI in medicine. They already have some great speakers lined up for. So tune in on June 28th. I think that's going to be super interesting. And yeah, then I think we're going to get into the summer break, and I think we're planning to come back in September, late August maybe. Timelines are not yet set, also because I actually hope that we can get back to physical events again. So let's see. But that is the next and last event before the summer break, right? And with that, I think, let me check whether Günther is back, but I don't see him.
He just dropped a note in the chat, so he's back. I
Yeah,
think.
I'm back. I think my line dropped for a minute, so I'm back online.
Yeah, so if you want, you can just kind of come back to the question that Christian Pflug raised. I'm not sure if you've had a chance to hear me still repeating it.
Yeah, what was the question?
So the question was, now I'll read it just quickly. How important is the feedback from the so-called experienced physicians into the AI-based system for refining the handling of training data or real data?
Yeah, that is very straightforward and easy to answer. Is very important because we have in the auscultation use case, we have at least 2 experts listening into the same sound signal. And these are very experienced physicians. And in some cases, we even have 3 different opinions on the same signal to pick up the anomalies. And that knowledge obviously goes into the training and into the year. Yeah, it goes into the training.
Cool. All right. I think with that, I think some people already left us. It's already late, but I still would like to invite you all that are still up to for some networking. Usually those events now actually get to the most exciting part, which is beer and pizza and talking. With our virtual setup, we need to ask you to grab your own beer and pizza, but we definitely can invite you to some networking. So I pasted the link in here. Unfortunately not clickable. I can fix that in a second. Thanks so much for joining. Everybody that's just dropping, feel free to join one of our next events. Sign up for the newsletter on our website if you want to get notified. We usually send out an email up front. We also will most probably by the end of this week send out the recording of this event. And everybody that's up to, feel free to join us on WonderMe for some follow-up talks and networking. With that, I would say, Andreas, right? Thanks for our speakers, Mr. Samek, Sven, Schmeier from DFKI, and Günther. Really, really interesting talks. Super detailed. Thanks for joining at that late time on this busy morning, Monday afternoon. With that, I would say have a great rest of the week and see you in a minute if you're up to.